Welcome again to this session, and now we will listen Professor Dmitry Karpinsky, right?
Yeah.
And he will talk about structure and magnetic properties of SCM dots. It's difficult to say this. Bismuth ferrite ceramics across the rhombohedral and orthorhombic phase transition. So thank you for being here, and please, you can start.
Thank you, Paula, for introduction, and thank you all for organizing this nice conference online, but still we are together. My topic is structure and magnetic properties of samarium dot bismuth ferrite ceramics across the phase transition between rhombohedral and orthorhombic phases. So let's talk a bit about the initial compound bismuth ferrite. I guess you know that it belongs to so-called multiferroic materials. Multiferroic means it has simultaneously 2 or 3 ferroic orders. Which ferroic orders? Magnetic, electric, and elastic. Usually we operate with 2, electric and magnetic, and it's enough to consider this material as multiferroic. This initial material, bismuth ferrite, has quite high temperature transitions, electric and magnetic. Electric is about 1100 K. Then it goes from ferroelectric to paraelectric phase, and the magnetic is about 640 K. Then it goes to paramagnetic from antiferromagnetic. So the structure of the initial compound is rhombohedral, described by space group R3C. So it's polar active. It means we can switch polarization. The dipole electric moment aligned along the C axis of the rhombohedral lattice. And the main problem of this material that it's anti-ferromagnet. To speak about possible applications, we have to have both ferroic order active, electric and magnetic, I mean ferromagnetic, or at least with some remnant magnetization. In antiferromagnetic phase, we have cancelled magnetization remnant. And moreover, this antiferromagnetic structure is modulated. So it's quite long, it has quite long modulation period, 64 nanometers. So the idea of the scientists who operate with this material is to release remnant magnetization and to keep polarization, electric structure. And how we can do it? There are several ways. We use chemical substitution. So we have some experience with chemical doping of the initial compound bismuth ferrite. We substitute bismuth ions, which are located in A position of perovskite structure. We substituted iron ions with other transition metal elements, and we try to find some kind of balance to keep these ferroic orders active and useful for us. So let's speak about the system which was mentioned, samarium dot. Actually, we made a lot of solid solutions when we substituted bismuth ions by rare earth elements like lanthanum, praseodymium, neodymium, and so on. And we found that in general, the phase diagram looks like this one. So, say for praseodymium, I put it here. As a function of dopant content of praseodymium, we come from polar phase, R3C, to non-polar one, orthorhombic, through some intermediate phases. Intermediate, they are orthorhombic, but antipolar. So dipole moments aligned in opposition, yeah, to each other. And the most interesting thing is to find how the system behaves at the phase boundary, say somewhere here, when we have the coexistence of different structural phases. Why it's more interesting for us? Because the system becomes to be unstable. And some external stimuli like radiation, electric or magnetic field, or pressure external can switch the structural state. And this is the way how we can manipulate the physical properties of this material. And we know then we come through this phase boundary from one crystal structure to another one. We have the quite strong modification of the unit cell parameters, regardless how we initiate this phase transition, via chemical doping or via temperature increase. So these slides show how the volume cell value change with the temperature, and the difference between the different structures, I mean, difference in terms of unit cell parameters is 1 or 2%, which is quite strong or quite big value. So let's talk about samarium. Why we choose samarium? Okay. One of the reasons that this is the last rarest element, last in the row of rarest ions, starting from lanthanum, when we still can stabilize antipolar phase, PBAM, describe this space group. And the next element for the solid solutions doped with next rarest elements with small ionic radius. For these compounds, we couldn't find antipolar phase. So they go immediately to nonpolar. And the idea was to keep active this antipolar order. So we clarified the concentration ranges of the phase stabilities for R3C phase. And I guess I have some sketches of the unit cells. This is rhombohedral one, and the metric is written, and the concentration range of the stability of this phase is also mentioned. Next, we have this antipolar orthorhombic with quite big unit cell, big as compared to ideal perovskite structure, perovskite cell. The metric is written. And next, as a function of dopant content, samarium in this case, we go to nonpolar phase. So as I said, this is general picture. The difference, if we speak about different rarest elements, the difference is in the concentration ranges of these, when these phases are stable. So we found that for compounds prepared by conventional solid-state reaction method, for samarium doped compounds, the concentration range of the stability is about only 1%. 1% means that only this compound, then we have 14%. 14% of samarium content it has, and it can be considered as single phase orthorhombic. So for me, it's okay, probably not for me, but it's quite easy to think that if the concentration range is so narrow and it shrinks down to 1%, it's quite natural to consider that the stability of the phase is really low, and we can shift it somehow with some external stimuli. So what we have here, this is diffraction pattern for the compound with 11% of samarium content prepared by conventional solid-state reaction method. And the natural question arises, if this phase coexistent, which I mentioned here, sorry, from 11 to 14% of samarium content, if this concentration range is natural and intrinsic to the system, or it's a function of our preparation method and the function of preparation conditions, I'm pretty sure that for the given synthesis method, this is the real function of this system, the real property. So it's intrinsic, I mean, this phase coexistent. And how to prove this? Okay, let's look on the X-ray pattern refined using two phases. As it was mentioned before, this one is rhombohedral, R phase so-called, and another one is orthorhombic, antipolar. And on the diffraction pattern, you can distinguish these two different phases with upper rack positions, which I ascribe to R phase, and at the bottom to the orthorhombic phase. So we can clarify the phase ratio for different compounds. And on the insert, you can see that some reflections which can be ascribed to either one or second phase, they change with the concentration of the samarium. And we can clarify, say, this particular reflection belong to the O2, this antipolar phase. And say this splitting and the left shoulder of this reflection belongs to the R phase, so polar phase. We can estimate the evolution of these phases inside this phase coexistence region. And again, back to my question. If it's intrinsic state, the phase coexistence, I would say we are pretty sure that it's intrinsic state. Why? Because then we start to heat the sample up to some elevated temperature, like 400 by Celsius scale. We found that the crystal structure, which we considered at room temperature like two phases, it becomes to be single phase. So we have to keep in mind that there is no ionic movement, ionic motion, and there is no any change in chemical composition. There are quite low temperature for this. But in any case, we can prove that the crystal structure changed from two phases to one phase, to single phase. And what's more interesting, that it goes from the structural state described by coexistent phases R plus O2, and it goes to not monotonously, I would say. The phase coexistent, one can consider, and it would be probably easiest way, that one phase decreases and another phase increases. I mean, the amount of the phase. But it's not the case. The system behaves in a bit strange way, I would say. And if we, at room temperature, have O2 phase, at higher temperature, we have O1 phase with completely different metric. And this is quite interesting. So this kind of proof that we have phase coexistent state, which is natural for this system. For the next slide, I guess we have another composition inside this phase coexistent state. And it's also possible to trace the evolution of different phases by concentration, by the content of the dopant element. And we can clearly say that it's the phase coexistent region is shrinked to 4%, 4 or 5, more or less. So this is natural state for this system. And let's check how the properties change as a function of samarium content. On this slide, you can see the isothermal dependence of magnetization. And it was quite natural to consider that then we have for rhombohedral pure phase, single phase rhombohedral state, the magnetization is, random magnetization is nearly cancelled because of this modulation. And then the content of the orthorhombic phase increases. We have monotonous increase of remnant magnetization. Yeah, and for the compound with 14% of samarium content, we have some loop, hysteresis loop. It's really small magnetization. Okay, this can be a question why we have released remnants inside antiferromagnetic state, but it's not strongly collinear. There is some really small inclination because of Toloshinsky-Moore interaction. And this is the origin of really small, but it still exists, remnants. So looking at this slide, I would say, okay, probably rhombohedral state is characterized by nearly zero remnant magnetization, and the orthorhombic state is described by non-zero magnetization. And the evolution of the isothermal curves show this smooth change of the magnetization, more or less in accordance with the amount of the orthorhombic phase. The more orthorhombic phase, the higher magnetization we have. Okay, and it's quite convenient to describe the correlation between the crystal and magnetic structure of these compounds. What we made with our colleagues then, we considered to synthesize new compounds with different methods. The previous compounds were synthesized by conventional solid state reaction, and we also made new compound using Zol-gel method with our colleagues from Belarus University. And we tried to estimate if something changed in terms of the phase stability regions. And I would say yes. In general, the evolution is the same. I mean, as a function of samarium content. In general, it goes from rhombohedral to nonpolar orthorhombic. And on the insert, I guess on the next slide, I have this enlarged. Yeah, here. And on the insert, you can see, okay, at low content of the samarium, we have a pure phase rhombohedral structure, like for ceramic compounds. It's nothing special. Then we increase the amount of lanthanum content, and as was predicted, I would say, the new reflections appear, and this reflection are ascribed to antipolar phase, like in ceramic compounds. But the concentration range are different. And what's more interesting is that we couldn't find the compound having single phase antipolar orthorhombic state. We always have some phase coexistence, either R plus O2 or O2 plus O1. And these concentration ranges are shifted a bit. Okay, this is quite natural because the another synthesis, another morphology of the grains, and average size of the grains are 100 nanometers or 200 more or less, as compared to grains when the compounds prepared by ceramic methods. Then we have microns. And okay, this can be, this is understandable. So the main difference, I'd like to emphasize that we couldn't find the compound having pure single phase antipolar orthorhombic state described by P, B, and M space group. So then it goes to, I mean, as a function of samarium content, then it goes to nonpolar, and it's distantly seen here. What we'd like to compare, okay, let's see how the magnetic properties change with the dopant content. We saw for samarium, for ceramic compounds, and it was possible to find a single match between the crystal structure and magnetic structure. For samarium compounds prepared by Zol-gel, it's not so trivial, it's not so distant evolution. So this is isothermal curves for rhombohedral, 8% of its single phase rhombohedral, then it goes to antipolar 14, then it goes to nonpolar with quite big coercivity. And let's put them on one side, I guess here we have. So what I'd like to focus on is that, say, compound having 12% of samarium content, which is, let's come back to here, which can be considered as single phase rhombohedral, yeah. Let me remind you, for ceramic compound, we already have some phase coexistence for this compound, for 12% of samarium. So 12 is still rhombohedral, but in terms of magnetization here, we have some released remnants, and but the crystal structure remains rhombohedral. So there is no, for this series of compounds, there is no single match between the crystal structure and magnetic structure. This is quite, I wouldn't say strange, but it's interesting. And we have to explain it somehow. So what next we made the idea, yeah, as explained, the idea to prepare these compounds with samarium and to play on this phase boundary region was to make, like we used to say, metastable state, yeah, metastable because it's began to be unstable under some external stimuli. And what we made, we applied high pressure to the compound. High pressure is 5 gigapascal. And what we found, looking at the crystal structure, that there are some drastic changes on the X-ray patterns. And say for compound which was rhombohedral, 8% of even 12, the structure, okay, the peaks are really broad, and it's not easy to refine the crystal structure. Why they become broad? Okay, the easiest way to explain, because the compound, the compound characterized by huge stress. Yeah, the grains are under stress, and this is a natural way to explain why the reflections are really broad. But let's look on the particular reflections of the satellites, not basic perovskite reflections. Say for a compound which is orthorhombic, non-polar orthorhombic, mainly I would say the crystal structure remains the same. This is still orthorhombic, and we have some particular reflections which prove this. This reflection is tiny. I guess this is from this parasitic reflections from the sample holder. So, but what's interesting that for compound which is characterized by antipolar orthorhombic, BNM, which we consider as meta or okay, like metastable, we don't have this for compound after application of high pressure. We don't have some specific reflections which were before high pressure. And this is interesting. And the question arises, if we can destroy this, I would say, intermediate phase, because this is antipolar orthorhombic phase is considered as intermediate between two more stable phases, more stable non-polar orthorhombic and polar rhombohedral. And in between in terms of concentration and in terms of temperature, we have this intermediate or bridge phase. And the question, if it's, what is the stability of this phase? And under high pressure, we can consider that it goes to the crystal structure of this compound, goes to some other symmetry, and using this diffraction pattern, we cannot clarify what is the symmetry of this, because the reflections are really broad, but we can say that symmetry changed. Okay, I'll try to save some time. So let's go further. And let's see how the magnetic structure behaves for the compound subjected to high pressure. the magnetic structure changed, and changed drastically. On the slides, you can see the compound which was and which is rhombohedral before and after high pressure. After high pressure, we have released remnants and quite huge coercivity. The same story for other compounds. We didn't check up to now. We didn't check all the compounds we prepared. It takes time. But looking at this data, we can say that most probably we change at least magnetic structure. I'm not sure about the crystal structure, but for these compounds, which are considered to be rhombohedral, we change at least magnetic structure. Why? That's the question. Sorry. Yeah, here. When we made CM measurements, what we saw? The first idea to explain changes in magnetic structure was, okay, we probably crashed the grains, crystallines, by high pressure, and because of uncompensated magnetization of the phase boundaries, we increase remnant magnetization. But it's probably not the case, because what we see on the SEM images before, this is compound with 8% of the samarium content before and after, if you see my pointer, after high pressure. And this is the same for 12% of samarium. And technically, the grain size is more or less the same. The porosity, of course, decreased because we applied this high pressure. And most probably something changed with symmetry. We cannot distinguish up to now. We plan to make some other measurements. But the grain size remains more or less the same. So this is a question, open question up to now for us. What happened with the crystal structure? Because we see huge changes in the magnetic properties. So we've made PFM, and I guess in parallel session, and yesterday Denis Alikin presented nice talk about the PFM also, piezo response form macroscopy. I will not focus on these slides, just to explain how it works. And we've made measurements for compound prepared by solid state reaction, and it was quite easy and fine to resolve the grains. This is 12%, so this is the phase coexisting state. And we can distinguish some grains with nice patterns, nice image, and we can distinguish different phases. When we can get open loop, PFM, switching spectroscopy in different places, and then this is described to rhombohedral phase. And in other area, we cannot get PFM response, cannot open the loop. So this belongs to antipolar orthorhombic phase. On the same images, we also made EDS analysis, and comparing different grains, it was possible to distinguish a bit different chemical composition. A bit means about 1% of difference in the bismuth and samarium content, and it's enough to consider the grain having dominant rhombohedral R phase or dominant O2 phase. It's possible using the facilities we used. So this is loops which show the evolution of the PFM response as a function of samarium content. For 12, when we have nearly single phase orthorhombic, the loop is nearly linear. Yeah? So this is for ceramics. And for powders or for compounds prepared by Zol-Gel method, the situation is more difficult. Why? That's the question. And these images show the PFM contrast with a scale of about 2 microns. Yeah. Here we have big grains. This is 2 micron bar here, and the whole scan is 5 microns, I guess. And here, whole scan is 2 microns, and we have some blurred contrast. We cannot distinguish the grains and the domains. So this is either the problem of resolution. Denis in the auditorium can argue that it's not an instrumental problem. Or the domains are so small that we cannot resolve it because of technical limit. So this is some images which show that the average grain is about 100 to 100 nanometers and doesn't change drastically with samarium content. So I guess I'm quite close to the end. Yeah, if I have some couple of minutes. What I'd like to highlight. So we compared the same system prepared by different synthesis method, by solid state reaction and by Zoljar. The morphology is different. The general evolution of the crystal structure is the same. We go from rhombohedral to non-polar orthorhombic phase via intermediate range. But the concentration range are different ranges. And what we found that for compounds prepared by Zoljar method, we cannot stabilize, and I guess this is intrinsic property of the system. We cannot stabilize this intermediate antipolar orthorhombic phase. And probably this is natural because of the morphology. We also, morphology of the crystallines, we always have some phase mixture. And probably this is the answer why we don't see distinct PFM contrast. We cannot clarify precisely grains and the PFM domains because we always have some mixture of the phases. And again, this mixture is natural state, intrinsic state of the system. When we heat it up, I mean the compound and measure, say, X-ray pattern, we will see single phase state. And this is natural for the system. So some conclusions, more or less I tried to explain what are the main results. And I'd like to say thank you and thank to my colleagues which helped to make measurements in the frame of our joint RISE project supported by European Commission. So thank you, colleagues.
Thank you, Dmitry, for this very systematic work. Congratulations. It was very clear. I don't know if someone from the audience from this field wants to ask a question. Yes, Professor Anatoly, yep. You may.
The microphone is muted.
Yeah.
Anatoly, can you switch on the microphone?
I'm trying to do it. Okay. I did successfully.
It's okay.
Thank you. I would like to ask, what the idea you changed the many elements, samarium and all others, the table, Mendeleev table is very big. What the idea? What do you want?
Okay, yeah. So we started from the initial compound, which was ferrite, yeah? So the idea was to get...
What the address you want to
yeah, this is...
develop the device, some kind of what?
The initial compound, which was ferrite, is considered as multiferroic. So it has simultaneously electric dipole, electric moments and magnetization. But magnetization is remnant magnetization is cancelled because of the antiferromagnetic structure, which is moreover modulated. So the idea was to find the way, using chemical doping, to release remnant magnetization, to have active two ferroic orders, to have magnetization regardless of which one, regardless the origin of magnetization. The ideal case to have ferromagnetism, because the initial compound is antiferromagnetic. And simultaneously, we have to keep polar order. to keep it ferroelectric, the compound. So to play between this order and to get magnetoelectric coupling, I would say. Because we made also measurements for magnetoelectric coupling, that's another story. So this is the way for possible applications. Magnetoelectric coupling. We can change magnetic subsystem of the compounds and to get a response in electric system, or vice versa. It's like a sensor without some intermediate parts. Direct sensor for magnetic fields or for electric fields.
Sorry, but you see, no one number. What no one the efficiency or sensitivity or you see just words and words. But I'm looking for the conclusion. No any word, no any number. You're just at the beginning of the way, and you can't to get some the device expected device performance.
Okay. I'd like to say, we can consider that it's more fundamental work. And now, of course, we are forced to make something more applicable. But for me, it's more, fortunately, I can do this. More interesting to play on this phase boundary region and to see how the system behaves. Of course, we are quite far from real applications, but this is the way to explain how system behaves under some external stimuli. Of course, we can, in the conclusion, we can put some numbers of magnetization, polarization, and magnetoelectric coupling. But this wasn't the main idea of this talk. Okay. The idea was to show how the system behaves.
Okay, thank you. Thank you.
Thank you.
I understand.
Any other question?
Yeah, can I ask?
Yes.
I'm Vinay Kumar from India.
Yes.
Yeah, thank you, Paula.
Yes, please. We are
nice
here.
I have two questions.
Yes.
One is on slide number 12. It is
scroll down, number 12.
It is application of 5 gigapascal force and change in orthorhombic phase.
Okay, yes.
Slide
this
number
one?
12.
Can you see it?
No, you stopped the sharing. You need to share again.
Sorry. This?
Yeah.
Can you see it now?
Yeah,
Yes.
it is there. So
Okay.
my question is, you have powders in which all the crystallites are randomly oriented. Now you apply a force, use force, and then expect a change in your crystallinity, because you are saying that that antipolar orthorhombic phase is going out because of this pressure. If I understand correctly, this is the thing.
Yep.
So I could not visualize that in case of a crystal, when you apply a force, when all the unit cell are aligned, then we expect some change in the atomic position and change from one structure to another structure. But in a powder, when the pressure is applied from all the direction, equal pressure, and your particles are or unit cells are randomly oriented, how you expect a change in the structural from orthorhombic is coming or not coming? This is one question.
Okay.
Question is clear?
I'll try to answer and you'll see. So speaking about the probably preferred orientation of the crystallines, which can happen under high pressure, I'm pretty sure we still have random. Random because we pressed, we can induce some preferent orientation, but pretty sure in general, we have random orientation of the crystallines. About the crystal structure, yes, we are sure that we change the crystal structure. We cannot prove it clearly by some method like X-ray or TM or some direct method, but looking at the properties like magnetization, we're pretty sure that the crystal structure change. Crystal structure means the position of the ions, and as a result of the application of high pressure. So I'm pretty sure we don't have any preferred rotation of the crystallines, but the crystal structure changed, at least for this particular compound having 14% of mineral content.
Thank you. Thank you. Next question is not a question, only query. It is on slide number 18, in which you have
18?
1.8.
Okay, let's. This one? Oh, sorry.
Not next. This one. This one.
Okay.
Yeah. In the bottom, you have plotted three curves, which looks like a hysteresis loop curve. But in your axis Y, you have plotted D33, if I can read correctly.
Yeah, this is D33 piezoelectric coefficient.
Yeah, so if I understand, it is the piezoelectric charge coefficient, T33?
Piezo coefficient. Piezo coefficient, vertical component of the piezo tensor.
Oh.
Then we measured, when we used PFM, piezo response force microscopy, we can read D33. Okay, we can read several components of piezo coefficient, but more interesting for us to present this vertical component, D33. This loops drawn using arbitrary units, so not numerically.
Picocoulomb per Newton or
okay, it's quite difficult to recalculate in or put these loops using real scale. It's just to compare how the loops change with the concentration and how the loops change. I've put this note active and non-active area because this compound has two phases, and we're able to focus on.
And you are getting the maximum value in the case of middle. Okay, thank you very much.
Okay, thank you very much, and thanks again, Dmitry, for this very important communication.